Professor. So this is my third ColabC, where we will uh, we will transition into a professional PyTorch workflow. We will start by importing Torch NN and Torch NN and other Torch Optim for layers and advanced optimizers. We will also perform device check, and the code is designed to automatically run on a GPU if available, falling back to CPU otherwise. So this is what we have defined here. Once that is done, we generate the same synthetic database on our three variable non-linear equation. However, notice the change in the workflow. We immediately split our data into 80% of training data and 20% in the test data. And this allows us to train the model on one group of the data and validate its true performance on the another. So once that is done, to handle our data efficiently, we will use tensor dataset and tensor data loader. Instead of feeding the whole dataset at once, the data loader breaks it into the batches of 32. The batch size we have defined here, it will break into the batches of 32. This mini batch approach is more memory efficient and helps optimizer to find the best solution. So these are our training batches, this is our test batches, and it batch size is 32. So once that is done, now we will define our model architecture. This is the core of PyTorch way. We define a class called 3 layer net that inherits from the nn dot module. In the constructor, we define our layer using nn dot linear, and in forward method we define our data flow. We are using ReLU for the first hidden layer, 10h for the second, perfectly mirroring our previous mathematical designs. So this is what we have done. We have defined this class in the constructor. We have defined the nn dot linear and our activation functions, and we are calling ReLU 10h for our forward function. Now we will initiate the model and move it to our active device. We set up the MSC loss and choose the Adam optimizer. Adam is significantly more advanced than basic gradient descent because it uses adaptive learning rates for every single parameter, which usually leads to much faster convergences. That's why we are using here the Adams optimizer. This is optim.adam we are using for optimizer. Once that is done, we will automate the training loop. So our training loop is now much cleaner. For each epoch we iterate through the train loader. The process follows a strict 4 step pattern, where the first step is perform the forward pass, second step is the compute the loss, forward pass, and then compute the loss, and then third step is call optimizer zero grade, and so we don't accumulate old gradients, and then we will call the loss dot backward and optimizer dot step to update the weights. By 100th epoch you will see our loss drop to very low value. So if you will see, starting the training, the loss is 0.04 in the first epoch, and the last epoch it is dropped to 0.09. So from 0.04 to 0.009, that is a huge drop. So once that is done, while training is complete, we will switch the model to eval mode. We iterate through the test set to calculate the final metrics. The results are impressive. You can see the test R square score of 0.9963, meaning our model explains nearly all the variance in complex linear data. So in the final summary, in the Colab demonstrate the framework by using built-in classes like nn.linear data loader, how we have used it, and how we have built a highly optimized 137 parameter model that generates perfectly to unseen data. We have successfully completed all the assignment requirement using the professional class based implementation. We'll move on to the next collab in the next video. Thank you so much.